So, thank you. Okay, so we stopped last week with the definition of what a feed-forward neural network is. We defined it, or I defined it, as a function class actually, and this function class consists of functions of this following form. We have here this function f, f, right, from some input layer Rp to some output layer Ro, and the signal x is mapped to this guy here, and we start by transforming the input with a linear transformation, so matrix vector multiplication here, followed by some activation function. Activation functions were functions that typically act component-wise on this output vector. That leads us to, right, this is our first layer, H1, and so on. And this is something we pass through the same procedure again and again and again. We talk about, or typically people talk about deep if you have more than 3 layers, 3 hidden layers. Yeah, and so on. This is the definition we need later on. So the jth hidden layer is given by this one. Okay, so we start with this x and we pass it through until we are arrived at the output layer. And just for definition, we have here our h0 is x is the input, and f of x here in Ro is our output layer, right? This is HL. Okay, so just for notational reasons. Okay, so we all have a form of what functions we talk about. Yes, so next step is that we have a look at, oh, my computer is so slow today. Be patient. We are not in a hurry. We are before Christmas, so let's take our time. Okay, yeah, so we continue with a little like wake up, namely this one. You can use your votes and have a look at that. So I mean, once we've understood how these neural nets are built, we can already start and analyze that a little bit. And the first question that I would like to ask you is, having understood how these networks are, if we choose activation functions to be continuous functions, then feed-forward neural networks are also continuous functions. Is that correct or not? Easy wake-up question. Please vote now. Okay, so the first have already, yeah, voted. And we have a 17-0 for yes, this is correct. Ryan, do you also think it's correct?
Yeah, I can see here the clear majority.
Okay, so we have a majority vote here. I mean, actually, that's the good thing about math, right? I mean, you don't care about the majority, you care about the truth. And here, the majority and the truth coincide. So we see that feed-forward neural networks, if we choose continuous activation functions, are continuous functions. And if we go further and say, well, what if these activation functions are differentiable? Is a feed-forward neural network then also a differentiable function? Can we build derivatives in that function class? And we have again the next votings: 3, 5, 6, 7, 8, 9 to 0. Yeah, okay. So that, I mean, very easy wake-up questions that we have here. And and then I have a final question for you. And this final question is this one. So let's read through it. So consider we have a feedforward neural network with also continuous activation functions and with a one-dimensional output layer. So one-dimensional output layer. Then if we have an input x1 and an input x2, such that one input leads to 0 as an output and the other leads to 1 as an output. Then there is also an input x3, there exists an input x3, such that an output is 1/2. Okay, so if you got the question, is that correct or not? Yes or no? Read carefully. Yes, no. Is that necessarily true? Can we guarantee that there is always an output or not? Right, if we cannot prove it, we have to think about how could a counterexample look like, and that could be a very easy that should be a very easy counterexample. 4 to 6, no, it's not always true. No. Okay, I see. 5, 6, 11. Brian, what do you think?
But I personally think, since the activation functions are continuous, so if we have to if we have something 1 and some one output is 1 and one output is 0, then there should be an input for which the output should be should lie between, because the activation is continuous.
Yes, you're right. Very. I'm happy that you see that. I mean, you can even be more precise. You can even link. You can even connect x1 and x2 and draw a line between x1 and x2. And on this line between x1 and x2, you will find one signal that actually is any value between between 0 and 1/2. Right. I mean, so if you go from x1 to x2, right, actually, regardless which curve you choose, you will continuously go from 1 to 0. From 0 to 1, right, along that line, because it's a continuous function. And this is actually, I mean, this is important to understand a little bit what these feedforward neural networks can do and what they cannot do. And of course, you want to approximate non-continuous functions. If you decide, right, you want to approximate. You want to approximate a function that is actually non-continuous, because for one input you get 0 and for another input you get 1, and you don't want to allow values that are between 0 and 1, because you only want to, for example, for a classifier or whatever, you only want to have 0 and 1. But this is actually not possible, but only approximatively possible if you look at that. And yeah, I don't want to go much more into the detail of the structure of these feedforward neural networks, but you should have an idea that they are continuous, that they are differentiable if the activation functions are differentiable, and that all you want to do is you want to approximate other functions. And so approximation theory goes into that direction. There is one paper that we have uploaded on Moodle. It's from my former postdoc, Hao Shen, has been published at the CVPR, I think 2 years ago, where he looks a little bit more into kind of mathematical analysis of what the structure of feedforward neural networks is. So if you are mathematically interested, you might want to have a look at that paper. Okay, it's not relevant for the exam, right? It's just for your information if you think that this is interesting for you. Good. Okay. Yeah, I mean there is another famous example of an approximation of the XOR function, where they say that you cannot realize that with only one hidden layer, but you need at least 2, right? This is also an interesting example, but we will not discuss that here. What we would like to discuss instead is have a look at how we can train these neural networks. Right? And training these neural networks means we have a certain loss function, and we have our function class predefined. That means the number of layers and the size of the layers and the kinds of activation function that we choose. And then we want to train the network, or in other words, find a function that best suits our expected loss. And this is what we want to do here. So we have a loss function, may it be in the supervised or in the unsupervised case, doesn't matter. And finding the best feed-forward neural network out of a class of function, and we have to define the parameters of that class beforehand. So the size of the layers, the number of the layers, the activation functions between the layers. If you have defined that, finding the best function is equivalent to finding the best weight matrices. Right? They are called weight matrices. These are the linear matrices with which we do the multiplication from one layer to another. And this means that we actually want to minimize this function here, right? The empirical loss. This is the empirical loss. This is our training data xi, fxi, or in the unsupervised case, it would be 1 over n sum L yi f of xi, right? It's not so much of a difference because they are not the variables that we want to search for. What we want to search for are the weights, right? So the weights that are hidden here in that function that is a feed-forward neural net. And the question is, how can we do that, and what's the idea behind? And yeah, and actually what's behind is nothing else than a gradient descent method. It's actually a gradient descent method on the weights. And for those of you who have already heard a lecture or in optimization, you will probably start with gradient descent methods as the, let's say, most easy methods of minimizing a particular function. So my question here, without a slide to you, just to have an idea of how many of you have already heard something about gradient descent methods. Will you just give me a vote to see how much I have to go into the details here? So you already know something about gradient descent methods, 14, 15, right? It's 1 has nothing heard about gradient descent methods so far, okay? Okay, so you may want to look it up. I will still, like, for the notation issues, give you a very short, but I keep it short since all of you have already heard that, how these gradient descent methods actually work. And so I try to present them here in a nutshell very quickly. So the task is, you have a function f, and we stick to some, Rn to R, right? It's a real valued function, and the question is, you want to minimize. The task is to minimize here this f. Yeah, f. And well, let's stick to Rn. And you can think of, so assume that we have our Rn here. I can only draw in 2 dimensions, but this is our Rn, and we look at, let's say, level sets, right? These are level sets. These are curves where our function is constant. You may think of level sets of a mountain or whatsoever. Okay, and these are the level sets. That is all x such that f of x is a certain constant here. And if we say that this is here the minimum value, right? So this is the minimum value. The question is, how can I approach that minimal value? And I start at some point here. On this point here, I compute the gradient. And the gradient is actually something that, or here it's better. And the gradient is something, is a vector here in the same space than our function is defined. And it points into the steepest ascent of this function. Right, this is it. So if we compute the gradient, f of x points here in the steepest ascent of f, or equivalently minus the gradient points into the steepest descent. And actually, if you want to define what directions and steepest is and point in the direction, you implicitly talk about a scalar product, and here we talk about the standard scalar product. And in fact, if you want to draw that here, you have here the tangent curve or tangent line to the sublevel set, and you have here this direction, and this here is minus the gradient of f, and it points in that direction. And now if you move from x, you move to a new x by going minus this gradient. You have you go into the direction, but what you do is you choose a step size. Here, alpha is greater than 0 is a step size, and that leads you always going like downhill. And hopefully is that if you are here, your value here is smaller than the other one, and then you go downhill again. If you're here, you go downhill again, and then you would approach slowly, but good enough to your minimum. So these are the gradient descent methods, and training a neural network is nothing else than doing this thing in a very high dimensional space, right? For gradient descent methods here, we have the Rn is actually so we have the number of weights W1 to WL. We have all of these W's. I mean, this is a matrix in R, I don't know what, input P times, do I have a number for the dimension? L1 times R, and then we have L times O for the output layer. So it's really a huge space. This is what we do. Just the number of weights. Total number of weights. Yeah. Oh yeah, and this is something I always forget. So this is why I have written that here. This step size for the gradient method in machine learning is also known as the learning rate. Okay, so this alpha, this step size alpha is also known as the learning rate. And if you, I mean, there is a whole bunch of literature and ideas and yeah, hints and tricks and traits of how to choose an alpha. It's in practice, I would say that choosing a fixed step size is good enough. experiences that we have is with alpha is 0.1 is actually works quite well. I don't know. Ryan, do you have more experience in how choosing the step size?
Well, these step sizes are usually fixed, like 1 to power -3 or something like that. And
Yeah.
yeah, for simple problems, we don't need to change this.
Yeah. Yes, but you can if you want, and there is a theory behind step size selection. So if you look at gradient descent methods and step size selections, you find everything you need to fine tune your neural network once in a while. Okay. Good. That was, I mean, this is the idea. So all we have to do is we have to compute the gradient of our function, and right. And if we do that, we run into the problem of what we had in the very beginning of our studies, namely Jacobi matrices and the chain rule. And this is actually the secret behind everything. So this is what we need to have a look at and what we need to recall: Jacobi matrices and the chain rule. Okay, and I assume that you have all heard about it, but nevertheless we should recall it here rather quickly: Jacobi matrices and the chain rule. So what do we have? I mean, we stick to functions here from Rn to Rk for a while. So if we have a function, let's call it, why not f, from Rn to some Rk. Do I like the notation? Yes, I do. So, right, so f of x is right given by some first component of x, second component of x, and last component fn of x. And then if f is differentiable, which we all assume here, that everything is well defined and so on and so forth, then the Jacobi matrix is defined, I call it like that, Jf. It depends on some point x. And in fact, it's the linearization of your function at that point x. So it's a matrix of the dimension n times k. And we have the first derivative dx1, f1, and we plug in our x, and we have dxn f sorry, here's a k. We are mapping to rk. So moment, hold on. I always confuse this n and the k, but it's actually easy because the matrix also goes from, I mean, it's a function that goes from Rn to Rk, so it has to be of this size, n times k. So this is dx1 fkx, right? Ryan, am I still on the right track?
Yeah.
Gott sei Dank. Then b dxn fn of x until, sorry, this is 1. I And here we have d dx n of fk of x. Okay, so this is the Jacobi matrix, and we have the chain rule that tells us that if we have a function g that goes from rk to some rl, and we have some function h that goes from rl to some rm, right? We start with rk, and then we have rg that maps us to rl, and then we have our h that maps us to some rm. And if this function g is differentiable in x here, and if h is differentiable in g of x, but this is where x, and here g of x, where g maps to, then the function h concatenated with g that goes from rk to rm is also differentiable in x with Jacobi matrix. So the Jacobi matrix here of the concatenation of these two functions at this point x is the Jacobi matrix of G at point x, and then matrix multiplied with the Jacobi matrix of H at this point G of x. Right? This is the chain rule, and this is what we need. So we have here this matrix multiplication of these both Jacobi matrices. Okay. Are there yeah? Let's have some room for questions here, perhaps, because half an hour is already over, and we said that we want to have a short break. So are there questions so far?
Not yet.
Not yet. Okay, good. Then let's have a short break, 3 minutes break. Okay, good.
Yeah.
Then see you again at 10:18. Okay, so let's look at some of the examples that are important for us to understand how we train our neural network. And one example is, or one easy example is linearity of derivatives. That means if I have a function sigma a that goes from rk to rl, and x is mapped to some vector a times x. If I look at that function here, then the Jacobi matrix of this function sigma a of x is A, right? Independent of x, right? I mean, the function is linear, so a linearization of the function is the function itself. You can also compute that. You see that very easily if you look at the formula that A is the remaining thing, and that also means that if you have a function h, if this is some sigma A followed by some G, then the Jacobi matrix of H is A times the Jacobi matrix of G at that point, right? For all x. Right, this is just the linearity of the derivatives that we have. Easy example, but good and nice to recall. Next thing, let's look at our component-wise activation functions. So we had this. I also called sigma. Was it also called sigma? Yes, I think so. From R H to RH, and we had x that is mapped to sigma of x1 and sigma of xh. Right, and sigma here was, it's a slight abuse of notation because I name the component-wise sigma in the same way that I name the vector function sigma, but MATLAB also does the same thing. So is that? And we had here this sigma of t was a function here from looked a little bit like this thing t. So what we want to do is we want to compute the Jacobi matrix. We know that the Jacobi matrix of this activation function sigma at some point x is, this is clear, it's an h by h matrix, and the derivative here is the first function derivated after the first variable. This is sigma prime of x1, and the rest here is 0 because it does only depend on the first component here, the first function. So what you have is a diagonal matrix consisting of the derivative with each individual components inside. So this is the diagonal matrix here. Okay, because the individual components here of this function only depend on one component of the vector, one input component. Yes. So a little bit more tricky and interesting is actually, hold on, did I want to say something here? No. Is Okay. Yeah. So let's also look at a kind of easy, very easy loss function that we look at, and that we also need to build a derivative if we want to optimize our neural network. So if we look at the loss function that we had for the autoencoders, so the loss function compares the output of the net with our input in terms of sum of squares, sum of square loss. So for the output layer, so the loss for the output layer is this one here, right? This is our output layer, and the Jacobi matrix here is. Hold on, I have to turn that off. So what is the Jacobi matrix here of this output layer L for some point H, and this is here so how do we compute that? Okay, so we have norm of x minus h squared is the sum of the component xi minus hi squared. I is 1 to output layer. We say it has dimension O, so it's I is 1 to O, but it's the same with the input dimension in that case. So we can name it P, doesn't matter, right? The size of our vectors. So we have that the derivative d to d h I of this norm x minus h squared is, so what is it? All summons, only one summon is depending on this hi. So this is 2 times, and you have this minus sign, so it flips in the sum. So it's hi minus xi. Right? Good. Right, you say if I do something wrong, right? You'll let me know. Right?
Yeah, this is all right.
Yeah, thanks. So the Jacobi matrix here, JL, also has a very simple form here. Namely, it's nothing else than this guy here 2 times, and then it's hi h1 minus x1 h2 minus x2 and so on until h p minus xp. Right? So let's keep that in mind. This is an element in R1 times P. But it's actually the transpose of the gradient. Okay, right. And of course, I mean, depending on the output layer, we have different Jacobi function for training. But it's clear that the Jacobi matrix of the loss function should somehow play a role in how to train it. Question is, why do we change xi minus h into I cannot see that.
Well, this is in the second last equation that you wrote.
I cannot see too much of the. Ah, here again. -1 goes into the bracket. Patrick, thanks a lot. And therefore they change. Yes. Why is it x minus f of x? Shouldn't it be y minus f of x? I think x is input. Well, yes, it depends. So the question, x minus f of x or y minus f of x, it depends, right? If we look at an autoencoder, for example, we had that example with the autoencoder. You want to fit the output of your net f of x to the input, and you want to see how good can you find a function f that approaches your input. Remember, if you want to go for regression or something else, this x would be a y. Then you go for supervised learning. Well, and we are not talking about autoencoder. I mean, this particular loss function is the loss function for an autoencoder. Yes. There are other loss functions for supervised learning where you have where you have your output y, and then they are not for autoencoder but for something else. For example, classification tasks, which we are going to discuss either today if we are fast enough or next week before Christmas. Right, and then you will see other examples. Okay. Good. So that's it. This is the Jacobi matrix, and yeah. And now this is also an interesting example. It's rather easy, but it will somehow change your perspective. So we have an example, the multiplication with a vector from the right. So this is we have to look at that. Actually, what we have is we have a function. Let's see how I call it. Yes, mult x. So pay attention here. We have mult x, and mult x is actually a map that takes a matrix as an input and a vector Rm as an output. And I say, okay, so I assign a certain matrix W to the vector W times X. Right? So yeah. The unknown here, or the variables here, is not, the variables here is the matrix. So I fix my vector X, and I see what it does with a particular matrix if I multiply this matrix with X from the right. Okay, so let's, I mean, very, very easy example. Easy example is always, let's say, okay, so the matrix A1, A2, A3, and A4 is mapped to the vector A1 x1 plus A2 x2 and A3 x1 plus A4 x2. Right, example. So if I want to find a Jacobi matrix of that function, I have to somehow sort my input variables in a certain way. Right here, they are structured as a matrix.
So, Martin, there is a small question before we proceed, just related to notation. Why isn't the function called mult of W?
Yes, because x is the parameter of the function, and w is the variable, and you will not call the function according to the variable. Right? Mult w would be a function that I would be the multiplication with w. Okay, good. So So it's like that. So it's the multiplication with x.
Yeah.
And if we want to write down, so we know the output here in this example, the output is a vector in R2, but the input are 4 variables, and they are structured as in this matrix form: A1, A2, A3, A4. And what we have to do is we have to restructure that to some Rm times n, right, into some form here that is in R4, because it's actually a function from R4 to R2. Okay. And one way that this is typically done in engineering is the vectorization form. So you vectorize, that means you take the first column of your matrix, A1, your first column, A1, A3, and then you take the second column and just plug it below, right? So that very often this vectorization that you have already heard of, and that's something you can do. Yeah, why not? Let's do it. So vectorization form, vectorize, we have A1, A3, and then A2 and A4. And this here is somehow mapped to this. To this colleague here. And now we have a function from R4 to R2. And you can write down the Jacobi matrix here, Jacobi matrix of A1, A2, A3, and A4 is, and now let's compute it. It should be a 2x4 matrix, right? Because it maps a vector from R4 to R2. And the entries here are the first variable with respect derived to the first variable, and of course you have to derive with respect to a. So this is x1 here, right? Then you have the second here derived to a1. This is 0 because a1 does not occur here. Then you have the first derived to the second, but the second component here is a3. Oh, sorry, I'm getting confused. I also get so this is probably not.
But it is still fine. If we can first do row wise, maybe like x1 and then 0, then x2.
But the second component is a3. So this is an a3. This is an x1 here actually. Brian.
Yeah.
This is an x1. Okay, so let's. It's tedious, but it's not complicated. Okay, so we have ordered that in that way. So the second component is an a3, right? Yeah. And since the second component is the a3, we have to build the derivative of the second one. Ah, okay, I know what you mean. It was correct, right? Yeah. Okay, so the second derivative with respect to a1 is 0. That was correct. Yeah. And right, I was confused. Now now the first with respect to a3 is 0. The second one with respect to A3 is x1. The first one with respect to A2 is x2.
Yeah.
The second one with respect to A2 is 0. The first one with respect to A4 is 0. And here with respect to A4 is x2.
Yeah.
Right. So this is how we can do it with this vectorize embedding. Right.
Yeah.
But this somehow destroys the nice structure of the Jacobi matrix. So what we do is we choose a different way of restructuring these matrices for our purposes, and it's just a permutation of that. And let's do that again. So if we have A1, A2, A3, A4, and we want to map that to this vector A1, X1 plus A2, X2, and A3, X1 plus A4, X2. If we choose another way, I have called it in the lecture notes. How did I call it? I think pi that orders this vector in the form from the left to the right, the way that we read in Germany or whatever. A1, A2, A3, A4. Then the Jacobi matrix of that function here, and the Jacobi matrix here of A1, A2, A3, and A4 is of this form here. We have X1, X2, and X1, X2.
Yeah.
Right, that should be it.
Yeah.
And that's a little bit easier for us. It has a nicer structure. It's mathematically, there is no difference at all, but it's easier for implementation purposes later on.
Well, just a small comment. We forgot to write A in the lower left vector. A4, A1, A2, A3, A4.
Yes, sure. Yeah.
And then
So in general, sorry?
I'm sorry, yes, please proceed.
So formally we have this pi that stacks this matrix W into a W, right? If I say the W consists of these columns here, W1 transpose up to WM transpose, then this is mapped to W1 onto WM. Right? If this is the general way of doing that, then the Jacobi matrix of multiplication with a vector x is given by x transpose, x transpose, x transpose, and here 0. So it has such a kind of diagonal structure, and this vector with which I want to multiply just lies here on the diagonals. And this is a matrix here in R m times m by n. Right? I mean, it's not complicated, it's just a bit unusual, let's say.
So Martin, just one small question. Again, one question from the student, like, is W is the variable, then why not mult of W? Like the same question. So maybe we can write W in the subscript, maybe to show that it is parameter of the function, like, or because the notation is still not clear. Some.
Well, right. I mean, it's a okay. So. Why not noting it with W? Because W is not, so you know, if you have a function X is mapped to, well, okay. So let's look at it. If I look at matrix multiplication here with some vector X, it's linear in not only in X, but it's also linear in the matrices, and the function depends on X. Okay, the function depends on X, and this is why the dependency of this function here is X. Right, and if you prefer, if it helps you, then we are not then write it in that way. Right? X is a parameter of the function, but it's not the argument of the function.
No.
And the argument of the function is the matrix W.
Yeah.
And it is linear in these arguments. It's a linear function with W, because if I have W1 plus W2 times X, this is the same then W1 times X plus W2 times X. So it's linear in that function. And since it's a linear function, we know that the linear function does not depend on the input variable. And the input variable is W. And we see here that it only depends on the function parameters X and not on the input variable W. Okay. I'm sure that if you take some silent moment and think about it, it will be clear, right? It's just, it's not too complicated. You just have to stretch it in your head. Okay, so that was that was actually the most tricky part in all that thing. And now we have all the ingredients to go for to go for our gradient of the function that we want to go. And before we go there, we will have another break, right? For let's say until 51, 4 minutes.
Okay.
Yeah, so we're almost there. If we now look at the function that we want to compute the gradient from, namely this guy here, right? And we know that, or we see that the unknowns are the variables are the weights WL to W1. We can compute, I mean, the derivative with respect to these variables. If we say that the partial derivative here of f, if we denote the Jacobi matrix, so we look piecewise onto these weights. So let's first see what the derivative of this function with respect to the first weight matrix is. So we have the dw L of this f, and this is, so let's use the chain rule. The last function, the outer function, is dl. Right. So we have the Jacobi matrix using the chain rule, the Jacobi matrix of L, and L is evaluated at the, well, last layer, of course, what the output is. Right. So this is the, you know, the sigma of L, then the phi of W, L, and so on and so forth. So this is exactly the, yeah, I mean, why not doing it? So right, I mean, the point where we want to evaluate that is sigma L phi WL sigma 1 phi W1, right, applied to X, followed by matrix multiplication by the Jacobi matrix of the second function here. Jacobi matrix of, this is the last activation layer, sigma L, and then evaluated at the point phi WL phi W1 of X, right? Then followed by matrix multiplication, Jacobi matrix of right, and what remains here is we have the WL and we multiply that with the remaining vector, but we have to keep in mind that this is the that here the weights are the unknowns and not the vector that is coming in, right? So we have exactly the situation of multiplication from the right, because W are the weights we built a derivative on. So this is the Jacobi matrix of multiplication with this vector. Actually, this is HL minus 1. Right, everything that remains after the multiplication of WL. Right. So this is nothing else than the Jacobi matrix of the loss function, which actually is a line, is a very flat matrix, only one row. Here, what we have here is our output layer, HL. Then we multiply that with the Jacobi matrix of sigma L. And what we have here in the bracket is the WL multiplied by H of L minus 1. Right? And the last candidate that we have here is the multiplication here. So it's this matrix where the HL1 lies here in the rows multiplication, H L minus 1. Right, and then there are no weights, let's say beyond that HL minus 1, and so the derivative here don't have to be the derivatives for the other sides, right? Because the WL weights are only here, and so this is the differentiation of F with respect to the weight matrix WL. Okay. If we go further, or if we go for the next step, and we say, okay, so what is the next rule, the differentiation with respect to the next weight? So we have D to D, let's say WL minus 1 of F. What is that? And of course, and now we have go from the outer functions more and more to the inner functions that are there, and the derivative with respect to the second weight matrix F is, so we have to start from the outer matrix. So this is HL, also again evaluated at the last layer HL, then matrix multiplied with the diagonal matrix sigma L, and yeah, this is WL times HL minus 1. That's what we had. Then we have this linearity here. So if we go back, if we look at that, now we have to put the derivative here with WL times HL minus 1, and this is linear. So this is the WL matrix here multiplied with J. Right, it's a constant here, WL, because I'm not building the derivative with respect to WL, but with respect to WL minus 1. Times the Jacobi matrix of the second activation layer, sigma L minus 1, evaluated at WL minus 1, HL minus 2. Oh, sorry. HL minus 2. And again, times the matrix multiplication with the remaining vector that does not depend on WL minus 1 anymore. Right? Because HL minus 2 only depends on the weights, on the weight matrices L minus 2, L minus 3, and so on and so forth. Right, so in general, what we have is the derivative d with respect to the jth weight matrix of F is, right, so we have to build the derivative from the outer function to the inner function as long as the argument still depends on the weight Wj. And so this is the J L HL times, and then we have the sigma L WL HL minus 1. Then we have the weight WL here, multiply that with J sigma L minus 1. All we're doing here is the chain rule applied to the functions that our feedforward neural network consists of. WL JL minus 1, and then we have the WL minus 1 HL minus 2, and then it repeats, and we go to the Jacobi matrix here of this is the weight matrix coming in again, WL minus 1 times, and then everything here repeats until we go to the vector that does not depend on the weight Wj anymore, and this is the vector H J minus 1. Okay, so really the best thing is you try it out yourself. Right? You have all the ingredients here, and try to compute it yourself. Use the chain rule. See where the problems are. I mean, I think this is the best way to grasp it. I can compute a lot and draw nice formulas here on this PowerPoint thing, but I think unless you've not done it yourself, it will be hard to understand how easy it is. It's actually not difficult, the thing you have here. Right. So my advice to you is use the chain rule. You know everything that you need, and take some minutes, like 15 minutes in the evening or when you're in good shape, and try to do it on your own. Okay. So that's one thing. So we have the updates with respect to the different weights, and what we want to do here So here it's summarized again, so that you can also read it. So we have here is the typo. This should be WL minus 1 here. And so the gradient here is consists of these partial derivatives with WL to WL minus 1 and until our last weights. And we update the weights here iteratively with a gradient step and say that, okay, the weights Wj are the old Wj, and then we go minus the gradient step. Okay, and the gradient step is, so we have these partial gradients here, and we have to reshape them into matrices, right? Because I mean, we have this small issue in building the derivative with matrices, which we discussed beforehand. So we have to reshape it, and actually this is the pi j to the minus 1, right? This is just the reshape into a matrix, right? Because we, in order to build these partial derivatives, in order to form this Jacobi matrix here of this F, we have had an enumeration of the entries of the weights, and this enumeration has to be made backwards here in order to stick it together to a matrix. It's really not complicated. You have, I mean, if you do it, you see that it's not so hard. But I cannot do it for you. I think that's the point. I cannot chew it for you. You have to do it yourself. But right, this is actually the formula. Reshape it into the matrix form. Right. Yes. So I think let's go through it again on a higher level, or see what we have done. So there is this. There is, if we have this multiplication with a vector from the right, or if we want to build derivative here of functions that are here of this form, I have a function f, and the input of this function is a matrix. I mean, I think this is the main thing. So w some r m by n, and we put that to some rk, and the input is a matrix form. What we have to do is we have to reshape it. Reshape variables, right? And then we compute the gradient. Actually, this is not much more difficult than this. We reshape the variables. We compute the. Let's do it like this. Sorry. Right. So we have, if we have a function f generally from some r m by n to some r k, whatever, we have to reshape into some r m by n, then compute the gradient or compute the Jacobi, compute the Jacobian, then Well, I thought that I could actually go through that without going into Hilbert spaces and stuff like that, but it's still possible. So reshape into Rn by n, compute the Jacobian, then apply the Jacobian. This is what we have to do beforehand. We have to apply the Jacobian reshape into some Rn by n, compute the Jacobian, apply Jacobian to well, a vector, and then reshape outcome into some m by n again. Right, so you have to go the detour through this reshaping part. Actually, that's all. Otherwise, you cannot write down the Jacobi matrix in a nice way. Okay. Jacobi matrix needs the Jacobi matrix needs an enumeration of your bases you're in, right? Actually, and this enumeration is going through the different entries. There is a little bit more theory that is behind, but it really boils down to that thing. Okay, so we have this reshaping issue, but it's actually, and if we have this reshaping issue and we have solved it and we say, okay, so we can deal with matrix valued functions in terms of derivative of matrix valued functions by reshaping the matrices, we say that, okay, so the derivative of the function that we want to have is derivative consisting of, so we look at the different weights separately. We start by looking at the last weight matrix WL and say that, okay, so if we build the derivative with WL, what in this line depends on the WL? Well, everything that is here after this part. So the HL minus 1 layer does not depend on the weights that come afterwards, of course. So it stops here, but then we have the Jacobi matrix of the other functions, and this is the Jacobi matrix of the loss function here, and the Jacobi matrix of the activation function, and that's it. And then we only have the multiplication here with HL minus 1, and we iteratively go further from the output to the input layer and end up with this formula here. And then we can iteratively use the gradient step by restructuring our weights in that form. Okay, and then we have iterative updates, and the reason why they are called, why this is called backpropagation, is due to the following thing. So this is, so if we look at this net here, yeah, we're looking at that picture, and we say that this here is our input layer, and this here is the output. We start with the last weights. So these are the weights here, and we start with the last weights by updating them according to that formula here. And this partial derivative of the weights in the last layer depend on the HL minus first layer. So they depend on this layer coming here. This here is the HL minus 1 layer. And so you have to feed forward your signal. You have to feed forward your signal until the L minus first layer. Compute the weights, right? And then iteratively for updating the other weight matrices now. So for update the second matrix WL minus 1, this one here, you compute this gradient there, and then you see that okay, it depends on this layer, here, JL minus 1, but you also somehow look at what the change is in the weights WL minus 1, and they are here, and so you somehow back propagate the error from the output layer to the input layer. Right? This is where the name comes from. So actually it's starting. It's that you start with the last weights, and then you go to the second last weights and propagate this error back to the first layer. Right? And yeah, and typically you start by using random weights. So the weights that you choose before you go for the first iterations are typically randomly chosen according to some Gaussian distribution, typically, and then you start and hope that you. So yes, so there's actually not so much more to say on this backpropagation thing. And I think it's also a good time to stop because time is over. There are some questions. We can go to these questions, and we will start next week, or we will go next week through the multi-class approach and see how we can use such networks for training multi-classification problems, where we not only have an apple and a pear that we want to foresee, that we want to predict, but more classes. Okay, good. Yes, so that was it. Thanks a lot. And are there questions, Ryan? I haven't looked at it.
So actually, all the questions have been answered more or less. One was related to this organizational thing that Moodle is still not responsive and still not updated to the new browsers. Like it was the problem last year also, and it is still the problem till today.
Okay.
Yeah. So another question was related to this left and right multiplication and the effect on Jacobian, but I forgot the slide, so I could not because it needed the slide specifically, so that this was left unanswered. Other than that, all the questions have been answered.
So I mean, for all of them that are confused with this notation, okay, really, I mean, go and do the following thing. Take an easy example. So this is my advice to you. I need a black, actually I would need a white piece of paper. Right here. Ignore, I mean, what I'm writing here, ignore it. It doesn't have to do anything else with what is there. But take an example, an easy example where you say, so we go from R 2 by 2 to R. And I say that the matrix A, B, C, D is mapped to, I don't know, A squared plus 2BD plus, I don't know, forget it, plus C squared or 2C squared, anything, right? I mean, invent your function yourself. Do it and try to analyze that. And then you will see, if you want to write down what the Jacobian matrix here is or what the gradient is, you run exactly into that problem that you have to reshape it. And then you can do anything you like for reshaping. You can go A, B, C, D, you can go A, C, B, D, you can do whatever you want. But this is what I call pi, right? And it's not magic. It's just actually it's a kind of convenience of writing the things down. Okay, so all of them that are so try to build the derivative of that function f. What is it? Okay, and this function depends on A, B, C, D. And if I call this, if I pass it a parameter x and say that fx is a map from A, B, C, D to xa squared plus x squared b plus c squared, I don't know, then x is this then x is a parameter of the function. It doesn't show up in the derivative. And this is the same way of how I used mult x. because it's the multiplication of this matrix from the right-hand side. So I'm sure if you have a look at it, a closer look, you will understand better, and you will get some moments like, it's not so difficult. Okay, try it out. Don't be afraid. Thanks, and good luck. Stay at home, and see you next week on Monday before Christmas. Bye-bye.
Goodbye.